Hello and welcome to my QCE 2023 talk. I'm Stephen Diadamo. I'll be presenting the talk titled The Impact of Quantum Memory Quality on Entanglement-Assisted Communication. This is work between me and Janis Nutzel in the TU Munich. And yeah, thanks. Let's get started. So the topics I'll be covering in this talk are the following. Firstly, I'll define what I mean by quantum-enhanced networks. These are a bit different than standard quantum communication networks. So I'll specify exactly what I mean there. Second, we'll talk about entanglement-assisted communication in quantum-enhanced networks. Third, we'll define a communication protocol for entanglement-assisted communication within these quantum-enhanced networks. Fourthly, we'll review the analysis we've performed to benchmark this protocol over different network topologies and in different use cases. And fifthly, we will talk about an application we thought of in which we can apply this protocol to, and that is in the area of distributed computing. So firstly, let's review what a quantum communication network is. A quantum communication network is a lot like a classical communication network, except the messaging going on between the network nodes are quantum messages. Quantum messages are collections of quantum systems that could contain encoded information or be correlated quantum systems, which we call entangled states. And the structure of a quantum network can be different to accommodate different laws of physics that apply to quantum systems. That means it can contain different types of hardware or different types of connections between the nodes. So that's a quantum communication network. So now let's talk about quantum enhanced networks. Quantum enhanced networks are classical networks, meaning the messaging going around the network are classical messages, but include something quantum to perform a task that can already be done, but with quantum it aims to improve the performance. And some examples of this are using quantum entanglement to transmit classical messages, using cloud quantum computers through the internet, or using multi-party entanglement to reduce the communication resources required, for example, to perform a multi-party computation. Entanglement-assisted communication is the act of consuming quantum entanglement to assist in transmitting classical, or it is also possible to transmit quantum messages using entanglement-assisted communication. When we are performing entanglement-assisted communication, the entanglement resources have to be distributed within the network beforehand, and then they are consumed when a message has to be transmitted. And so this entanglement can be distributed ahead of time and stored in a quantum memory, or it can be sent right when it's needed and consumed immediately. And it depends on the use case and which strategy to use. So what does entanglement-assisted communication provide us? In some scenarios, entanglement-assisted communication can provide a communication rate advantage. And some of the scenarios are the following. They are the case when there's low signal to high noise ratio communication. Entanglement-assisted communication also provides an advantage in covert communication, where covert communication is this act of hiding the fact that transmissions are going on between two parties, so that between A and B, if there's an eavesdropper listening, the eavesdropper can't determine that communication is happening. And also multi-user communication, where the multiple senders share entangled states ahead of transmission, which actually it can enable them to communicate with a single receiver, where without entanglement, communication would have been impossible. So what is needed for entanglement-assisted communication? We need two primary things. First is we need communication hardware, and the communication hardware are things like entanglement sources, measurement devices, and quantum channels. So the physical devices needed to actually perform communication. And then we need a communication protocol, which instructs the hardware to perform the necessary actions to distribute the states at the right time, and also synchronize between the two communicating parties so that they're performing measurements in a synchronized way. So in this work, we've developed a communication protocol for entanglement-assisted communication for sending classical messages over a quantum network. So firstly, we thought about what are the necessary components needed to perform classical entanglement-assisted communication. And those are a classical message buffer, something to hold the classical messages, an entanglement buffer, something to track the entanglement that is being stored, a quantum channel, of course, for making the quantum transmission, and a measurement device to measure the outputs from the channel. And here's a depiction of the model. So firstly, we have a classical queue, which can store L bits of information, and messages of size J arrive into the queue. And there we have synchronized buffers for the entanglement. Connecting the entanglement buffers is a quantum channel. From there, a decision can be made to either measure directly from the output of the channel or the output of the channel can go into the entanglement buffer. From there, the messages are measured in the device, and a message of size j is output from the measurement device. This communication model, we've developed a protocol on top of this to achieve classical entanglement-assisted communication, and this protocol does the following. It processes the message buffer with a priority to transmit the message as soon as possible. If there are no messages in the message buffer to transmit, then the protocol should attempt to generate entanglement and then store it. If at the time of a message transmission there is entanglement available, then it should be consumed to perform entanglement-assisted communication, and otherwise, if there's no entanglement available, the message should be transmitted at the unassisted rate. And here's a decision diagram representing this protocol. So we see periodically at some inter-arrival rate, there should be an incoming job. If there is, then we look to see can it be stored in the classical buffer. If it can, store it, otherwise it's dropped. Back up to the incoming job. If there is no incoming job, then we go look to the buffer, which is the classical buffer. If the buffer is empty, then we try to generate entanglement by taking the yes path. We check the entanglement buffer. If that's full, do nothing. Otherwise, generate entanglement. If the message buffer is not empty, then we need to transmit the classical message with high priority. So we check is there enough entanglement. Then if there is enough entanglement, using entanglement-assisted communication rate. Otherwise, use the classical communication rate. In order to perform entanglement-assisted communication in practice, we need the following hardware components. We need a quantum source, we need an entanglement source, we need quantum memory, we need a quantum processor, optical switches, and measurement devices. And so with our model alone, we haven't described enough to analyze the physical layer. And so therefore what we've done is we converted our model of the queuing system and modeled it after a hardware model. And so the hardware model is the following. So I put the queuing model on the left. Let's see how it compares to the model on the right. So the message buffer is a classical message buffer. We don't need to do anything special about that. But what we do have is we have an entanglement buffer, which is represented by quantum memories. And connected to the entanglement memory buffer is an EPR pair source, which means something that can generate entangled pairs. That's also connected to a quantum processor, something that can modify the quantum state of those pairs. And we also have a qubit source in case there's no entanglement to transmit. We just need to transmit the classical message using a qubit channel rather than entanglement-assisted communication. And we have a quantum channel that's modeled after fiber optics. There's a switch which can route to another synchronized entanglement buffer on the receiver side, which is also connected to the quantum processor, or we can switch to go right to the quantum processor without going through the entanglement buffer. Output from the quantum processor at the receiver side is the classical message, and hopefully the classical message is the same one that went in from the sender, but due to noise, it's unlikely that it'll be exactly the same, and error correction would be needed. Okay, so we have the hardware model. We also use a memory model for the entanglement buffers, which are modeled after quantum memories. And the memory is qualified by its T1 and T2 time. And so specifically the model is the following. We assume that there's a quantum state rho, and it experiences noise for delta t seconds. And then the noise model is the following equations. So we have the definition for E0, E1, and P1. And then it goes through a quantum channel, which maps the state rho to the state written in step 4. After that, a subsequent channel is applied with the following equations. So we use the T1 and T2 time to model the secondary channel, which is given in equation 6. So in the summary of the analysis we used to benchmark our protocol are the following things. So we used a discrete event simulator called NetSquid. And then using NetSquid, we programmed a protocol using the hardware models provided by NetSquid. We then ran the simulation under various network parameters and gathered the statistics to see how well our protocol performed. We focused on the quantum memory properties in this analysis to see how the memory affects the communication rates and the error rates. And for now, we want to focus on the absolute best rates we can achieve. And so we ignored the link layer protocol, which means we would need additional communication steps to synchronize the users, but we focus on the physical layer, which would be the best case scenario, as there's no additional communication overhead. We bypass that using simulation. And then using the simulation outputs, we compute values like the average throughput and the error rates. The first network topology we considered is just a point-to-point channel. This is the easiest network topology we can consider, so we start with that. The network parameters we've used in this case, we assume that j is equal to L is equal to 4, meaning one message can be stored in the message buffer at a time. And we assume that the sender and receiver share a synchronized entanglement buffer of 200 memory units each. We then vary the T1, T2 times in our simulations, and we also vary the message arrival rate, so the rate at which messages arrive in the buffer L. We then vary the queuing practice in the entanglement buffer, so we vary from first in, first out, first in, last out, and then we have a different queuing practice where when there's a chance to generate entanglement, but the entanglement memories are full, we kick out the oldest entanglement units to refresh them with new ones. And then we have a polling rate such that at the absolute maximum of our simulation parameters, the link is a 400 megabit per second link at most. Here are the simulation results for the point-to-point analysis. First, I'd like to point out two important lines. The first one is the dashed black line, which represents the case when no entanglement is used in the protocol at all. That means every classical message is transmitted using qubits. The second line is the solid blue line, which represents the case when the quantum memories have no noise at all, meaning they're perfect memories. So anything in between the black dashed line and the blue line is an enhancement between the unassisted rate. So what we can see with the three orders of magnitude we've tested for the quantum memory noise is that the red case, which is 1100 and 1000 nanoseconds for T1, T2 time respectively, that up to around 0.2, the throughput is worse than the unassisted rate. That's the solid line. I'll explain the dotted line in a second. But when the magnitude is less, in the green and yellow case, the solid lines never surpass the unassisted rate. We tested the different queuing practices for the entanglement buffer. We used first in, first out, entanglement replacing, which is when the entanglement buffer is full, we replace with a fresh entanglement pair when possible. And we also tested first in, last out, which is the solid lines. So the first in, first out queuing practice shown to be the worst one, and we see that up to about 0.35, the decoding rates are pretty much random for all cases of the memory, meaning that the entanglement stays too long in the memory before it's used. In the first in, last out case, we see that it's a much better performance in terms of decoding bit error rate. And then when we add the additional part of entanglement replacing, meaning we kick out old entanglement units and refresh them, the decoding bit error rate has a vast improvement. And above in the average throughput, we can see that the red line surpasses the unassisted rate much quicker than the unassisted, using the entanglement replacing strategy. We tested another case when the classical message buffer was much larger, so 5 times more than the message size, meaning it can hold 5 messages at once. And we kept the entanglement buffer fixed at 200 units. And we redid the analysis in that case. And now we see a completely different set of results. So the dashed black line now very closely matches the case of perfect memory. The red line no longer surpasses the dashed black line in any case, and therefore there's no improvement whatsoever. What we see is the queuing practice still makes a significant difference, but none of the quantum memories had a good enough quality to surpass the classical rate. And there's only a small set of arrival rates that actually can be surpassed using entanglement, which is the part between the black dashed line and the blue dashed line in that little area near 0.3. In another set of experiments, we wanted to analyze how the size of the entanglement buffer affects the transmission rates and the decoding error rates. So we again reverted back to j equals L equals 4, but now we varied E. We fixed the T1, T2 times in this case, and then we vary the message arrival rate as well. The results of those simulations are shown in these plots here. And so we can see the difference between E equals 1, E equals 10, E equals 200, and E equals 0. And then we also varied the queuing practice again to see if that makes a difference. So what we can see is throughout these experiments, E equals 1, 10, and 200, the throughput doesn't change that drastically. But we can see that the decoding bit error rate actually changes quite drastically depending on the size of the buffer. So with E equals 1, there's only 1 unit of entanglement to be used, but the error rate is much, much lower than when there are 200 units of entanglement to use. And then when we use entanglement replacing strategies for the queuing practice, the decoding error rate can be significantly reduced, especially for low message arrival rates. what we see is even with 10 units of entanglement, we do even better than with 200 units of entanglement, especially with this quality of memory. So by increasing the quality of memory, maybe we can see significant improvement with E equals 200. But when we have noisy quantum memories, which is expected for the near future, using only few units of entanglement can actually be used to surpass the non-assisted rate seen in the black dashed line. The summary of these results are the following. We saw that in our cases, to surpass the unassisted rate, the memory T1, T2 time should be roughly 1,000 times higher than the polling time for the messages to arrive. The queuing practice played a big role for the entanglement buffer. And what we found is first in, first out performed the worst, but using a first in, last out approach while refreshing the entanglement units that are currently being stored with fresh ones when possible had the best performance. We also noticed that when more messages can be queued in the classical message buffer, the gap between the assisted and unassisted rate is quite small, and maybe there's not much advantage to gain in that case. And there's a point in which the entanglement buffer can be too big such that a smaller entanglement buffer would outperform the larger one, depending on the quality of the quantum memory. And so in the near term, we should look at minimizing the number of entanglement units we need while maximizing the performance. So up until now, we've been focused on the point-to-point channel. And although that's an interesting analysis, we would like to see a more complicated scenario in which is network communication. And now we make the topology a little bit more complex, and we look at network entanglement-assisted communication. So in this next set of experiments, we've defined this topology, which is a source sending messages to a destination. The source has synchronized entanglement buffers with two middle nodes, and it uses the classical message buffer in the same way that we've seen before. The messages arrive, and we use the exact same communication protocol as we defined before as well. The source has to make a decision to send messages to the top node or the bottom node. And the way we've defined the routing approach in this case is we use the route that has the most established entanglement at the time of transmission. The analysis we've performed is exactly the same as before. We vary the quality of the memories, and we vary the message arrival rates. And then we see how does this network transmit messages from source to destination, and we analyze the throughput and error rates again. The results of our analysis are shown here. So again, we've analyzed the case with the perfect memories, which is the solid blue line, and we investigated the case when we don't use entanglement anywhere in the network, which is the black dashed line. So what we see here is in the upper part with the average throughput, a couple of interesting points. The first is that the red line representing the case when the quantum memory has a T1, T2 time of 1100 and 1000 nanoseconds respectively, it surpasses the unassisted rate a lot sooner than it did in the point-to-point channel. Another thing of interest is that the green solid line, which represents the T1, T2 time of 110 and 100 nanoseconds respectively, does surpass the unassisted rate at high message arrival rates. So what we think is that with a weaker quantum memory, we could see an advantage. In the lower plot of the decoding bit error rate, we again tested the different queuing practices, and again, using this entanglement replacing strategy greatly improves the decoding bit error rate. So to summarize these results, we can see that in a network setting, there could be more options for routing, meaning there are multiple paths to the same destination from a single source. And what that means is there could be more links with more idle time, leading to more chances to generate more entanglement. By using different routing practices, we can think about using a route that will maximize the amount of time links have to generate entanglement, and at the same time use the routes that have the most established entanglement, making use of the entanglement-assisted rates as often as possible. And what we saw is that the memory quality in this case could be reduced to surpass the unassisted rate, given we're using the best queuing practices for the entanglement buffer, as well as sending messages at a high enough rate. For the last part of this talk, I want to discuss an application we found that we think could be a well-suited application that can implement this protocol of distributing entanglement while idle and then using that entanglement to send messages at a higher rate. And that application that we found is in distributed computing. The computing scenario we consider is the following. We consider a computing center with a collection of processing nodes. These nodes form a network, and they perform distributed computing with each other, and they process an algorithm collectively, but on the same input. So in order to perform an algorithm on the same input, these nodes have to pass messages to each other, and they have to pass messages periodically because once these messages are passed, there's this time of idle when computations are made, and then more messages are passed, and then more computations are made, and this process repeats. So what we see is that there's this idle time when these computations are being made, and we thought, what if the nodes could distribute entanglement during the time in which they're making computation? And this way, when the messages have to be transmitted, they can be transmitted at an accelerated rate using entanglement. So we wanted to test this, and we thought of a particular algorithm which we thought was well suited for this. And that algorithm we thought of is called k-means clustering. It's quite popular in machine learning. It's an unsupervised learning algorithm that works more or less like this. To start, we're given a data set with the initial centroid points. And the initial centroid points are a guess to where the data points are clustered around. And then we get the labels of those points according to their closest centroid. Then what we do is we update the centroid points to be an average of the locations of the labeled data points. So we measure the distance between the centroids and label them as the closest neighbor. And thirdly, we iterate this process over and over again until the centroid points converge to a single point. When we take that to a distributed setting, we're given the same initial conditions. We're given a data set with initial centroid points as a guess. And then what we need to do is distribute the data points between the processing parties and also distribute the centroid points between the parties so that they know where those centroid guesses are. Then what we do is we perform an iteration of labeling. So each node gets a fair share of data and they compute the distance to the centroid points. Once that's done, they broadcast the computed labels to all the other parties so that all the other parties can update the centroid points locally. And then what they do is they iterate this process until the centroid points converge to a single point. There are other ways to perform distributed k-means clustering, but this is the way we found made the most sense for our scenario. So now what we do is we consider the scenario with the distributed k-means clustering, and now we took two nodes performing distributed k-means clustering together using this point-to-point analysis we've considered already. And during the time in which they're constructing the labels, that is measuring the distance between the centroid points, we use that time to, in parallel, distribute entanglement between the two nodes and store it. And then when it comes time to broadcast the labels, they use up their entanglement to increase the transmission rates, which allows the computation to go at an accelerated rate if we can reduce the amount of time communication takes. To measure the quality of the algorithm, we use the following things. We use firstly the F1 score against the true labeling. The F1 score is defined as seen in step 7, which is the precision and the recall multiplied together divided by the precision plus the recall, all multiplied by 2. And then we also track some communication resources, which is the number of total messages transmitted to complete the algorithm for 10 iterations of the algorithm. And then we use 500 data points with a binary labeling, and we test it over different qualities of memory. Here are the results of performing this distributed k-means clustering, where during the idle times we used the time to distribute entanglement between two nodes. On the left, we track the F1 score. On the right, we track the number of total transmissions. We track the total transmissions using the black dashed lines, and the solid colored lines represent different qualities of memory with the associated F1 score. On the x-axis, we measure the number of EPR pairs that were sent between iterations of the k-means clustering algorithm. What we can see in the total number of transmissions is that if we increase the number of EPR pairs sent between iterations, the total number of transmissions is reduced. And what that means is we use fewer messages to send the same amount of data between the nodes. Although this relies on the quality of the entanglement. And so what we can see is with weaker quantum memories, that is the blue line, for example, which represents the quantum memory using 1100 and 1000 nanoseconds for the T1, T2 time respectively, the F1 score quickly diminishes, and at around 120 EPR pairs between iterations, the output is almost essentially random. What we see is if we can improve the quality of the quantum memory using the red line, which is a 10 millisecond T1, T2 time, the number of transmissions is reduced, so we gain a computational time reduction. by reducing the communication resources. And at the same time, we have a fairly decent F1 score, which doesn't have as severe impact due to the noisy quantum memory. So with all of that analysis, I'll make the following concluding points. The first is that entanglement-assisted communication could provide an advantage in communication rates with noisy memories, but quantum memories that are of high quality, even if they are noisy. And so there is a threshold in which the quantum memory is too noisy to surpass the case when entanglement is not used at all. The protocol in which we use to generate and distribute entanglement and then consume it later will play an important factor, especially the way in which the queuing practice is implemented to extract the entanglement from the memories. But using the idle time between transmissions to generate and store entanglement can both increase the network utilization, reducing idle time in the network, and also decrease the communication cost for classical messaging by using the entanglement-assisted communication rates of the channels, which can boost the overall transmission rates. And so with that, I thank you for your attention, and I'm happy to take questions about this research. Thank you.